Right. Good morning, everyone. Today we are discussing the practice paper 21. Okay. In this paper, we are discussing chemical calculations essay from 2024 A-level paper. Okay. So after discussing that essay question, calculation essay question, we will do 12 MCQs which you can attempt that are given in 2025 A-level, the recent A-level paper, the MCQs. Okay. So from unit 1 to unit 4. Right? So let's start the discussion from this calculation essay. So I'll show you the essay question. This question actually is kind of a little bit different from earlier questions we did. You can have that experience because we did several questions now from 2018, 19, 20. Like that we continued this essay question. But if you look at this question, this particular question, you will feel that it is kind of checking more into that theory area or more into applicable theories are checked here. Right now, look at the question. So the main compound present in iron pyrite is FeS2. Iron pyrite is a metal ore. Metal ore is something that we get from the earth. Okay, so FeS2. Then a 1.5 gram sample of iron pyrite was oxidized under the laboratory conditions, and all the sulfur in FeS2 was converted to sulfate. Okay, so they are doing some redox reaction. Okay, you don't need to think about what is the oxidation number of sulfur in FeS2. That part is not needed. You can just simply understand in FeS2 you have two sulfur atoms now. Those sulfur atoms are converted to sulfate. That means it is giving you two sulfate from one FeS2. Is that clear? That's what you need to understand. They are not expecting a balanced chemical equation. So if you check the questions they have asked, see the first one, calculate the weight percentage and then calculate the percentage of FeS something. Now they are asking about calculations. So they are not inquiring any balanced chemical equation. That's why I said this is more directed towards the applicable things. Okay, so it's kind of different from earlier calculation essays, right? So now, however, it is telling FeS was converted to FeS2 is converted to sulfate, right? Then the resultant sulfate was precipitated as barium sulfate. That's a common thing we saw in earlier questions. Every time we get sulfate time, we precipitate that one using barium, right? And then it gives you barium sulfate. So equal moles of barium sulfate are given. Understood? And then the dry weight of barium sulfate obtained was 4.66 grams. Okay, so that's the data they have given. So they're asking the first question, calculate the weight percentage of FeS in iron pyrite. So like I said, all sulfur atoms in FeS are converting to sulfate. That's what you need to understand. No need to balance this one. Okay, don't try to balance even. Right now, however, this sulfate is precipitated by adding barium as barium sulfate. Barium sulfate precipitate. So 4.66 grams. 4.66 grams. Right now, we're going to start the question. The part one, we're going to start by checking the number of moles of barium sulfate. That's what we need to start now. It's obvious because at the later part in the question, they have given the relative atomic masses of oxygen, sulfur, iron, barium, those elements too. So obviously, you need to start from there. Understood? You need to start from there. So here we are getting 1.5 grams of sample of iron pyrite. Okay, that also you need to calculate the weight percentage. Okay, now this is how you need to do. First of all, find the molar mass of barium sulfate. Molar mass of barium sulfate. Okay, for that you need those relative atomic masses. 137. It is given here. And then sulfur 32. 4 oxygen means 16 into 4. So if you add them, you will get 233 grams per mole. 233 grams per mole. Then you need to find the moles of barium sulfate. Moles of BaSO4. So simply divide this 4.66 grams by 233. So you will get 0.02 moles. It's divisible, see? It's divisible. Exactly 2 times. Okay, 0.002 moles. Then you need to address this stoichiometry thing. Okay, so therefore moles of sulfate is what? Moles of sulfate given is same, no? That is also 0.02 moles. So for this one, if you need, you can write a reaction. Balanced chemical equation you can write for this one. Like this. Okay. SO4 2 minus is added with barium 2 plus to give BaSO4. Then you can write 1, 1, and 1. These are the other ratios. Okay. And then you can show this relationship. Now we are not going to write a reaction for this. No? So simply write 1 FeS mole, FeS2 mole gives you 2 sulfate moles. That relationship you have to write because here you have 2 sulfate atoms. Those 2 sulfate atoms are giving 2 sulfates. That's the idea. FeS, or you can say FeS2 1 mole gives SO4 2 minus 2 moles. 2 moles. Okay. So therefore, moles of FeS2. So if you are not writing an equation, you need to give at least a sentence. Okay. That must be done. And then 0.02 divided by 2. 0.01 moles of FeS2 is produced. Now we need the mass percentage of FeS2. In order to do that, you need the mass of FeS2, right? So before that, we need to find what? Molar mass of FeS2. Okay. So then molar mass of FeS2, to find that, we need the relative atomic mass of iron and sulfur. 32, 64, 64, then 120 grams per mole. Okay, so then let's find out the mass of FeS2. Mass of FeS2 is equal to 0.01 mole multiplied by 120 grams per mole. So it's 1.2 grams. Then you can find mass percentage. So 1.2 grams. The total mass of the sample is 1.5. No? So out of 1.5 gram sample of iron pyrite, you have only 1.2 grams of FeS2. That means others are impurities. Understood? So then I multiply by that one by 100. Okay. So it is divisible. You can divide this one by 3. Then it will become 0.4. This will become 0.5. 0.5. That means 80%. You will get 80% as the answer. Is that clear, Laman? So how many of you got 80% for this one? Can I see hand raise? Right. Now let's go to the next part. I'll show you the question. So in part 2, it's asking something like this. See, first of all, there is a small paragraph. So it says, FeS in 20 grams of iron pyrite was subjected to oxidation by soil microbes under natural conditions for 120 hours. Under natural conditions for 120 hours. Okay. And this oxidation reaction is represented in the following equations. Now, earlier part, it described about the laboratory condition. Okay. And this one is telling about soil microbes. So it's something natural condition. Okay. So naturally also you can do this conversion, that conversion of FeS2 to subjected to oxidation by microbes also. Right. So the reaction is also given. FeS2 is going to ferric hydroxide and sulfuric acid. You can see the ratios here. Okay. 4 FeS2 is giving you 8 sulfuric. That means 1 FeS2 will give you 2 sulfuric, just like earlier. Ultimately, it is giving you 2 sulfate. Okay. And it is telling the sulfuric that was produced in this reaction after 120 hours was quantitatively separated and precipitated as barium sulfate. So the same procedure is followed. All the sulfate ions here is precipitated as BaSO4. Okay. The dry weight of barium sulfate obtained was 31.13 grams. Okay, so because we are using more grams, no? So earlier we used 1.5 grams. For that you got 4.66. But now we are using 20 grams of iron pyrite and we are getting 31.13 grams of barium sulfate. Okay, so then what they're asking is calculate the percentage conversion of FeS2 in iron pyrite to sulfate after 120 hours by soil microbes. So they have given an equation for that too. Then you can understand it more. Experimentally obtain mass using soil microbes and theoretical mass. That's how you calculate the mass percentage. Now, you can do this one in several ways. Okay, but let's do like this now. Let's find out how much FeS2 in the sample was converted actually into sulfate. That's what they're asking. Okay, so I'll explain that in the board. You will understand more at the end, and I'll show this question part again and tell the same thing one more time. Okay, so now let's try to understand this. Like I said, this question is more oriented towards the practical application. That's a good thing they started, because no matter what the calculations you do in real life, in real laboratory experiments, you are doing things like this. Okay, so then you must have practice for that. Okay, so I'll explain that more. Now here's what they are telling, right? So there is a sample of iron pyrite, 20 gram sample. Okay, so mass of iron pyrite, 20 grams. Now, even though iron pyrite you have 20 grams, it's not all composed of FeS2, no? Isn't it? So FeS2 mass is only 80% of that sample. You found that earlier. Remember, only 80%. So let's find out mass of FeS2 in this sample. So how much FeS2 is there? Only 20%. So 80%. Multiply by 80 over 100. So you'll get 16 grams. 16 grams of FeS2 is there. Understood? So that's the theoretical mass present. Okay, so this is what we mentioned as the theoretical mass of FeS2. Theoretical mass. So we hope all of this FeS2 is converting to what? Sulfate. Okay, so that's what we are expecting, but actually it may not happen. That's why we are asking a question like this. No? Only a part of this FeS2 will convert to sulfate. Understood? Only a part of this FeS2 will convert to sulfate. Now let's find out that. Okay, it's telling we obtain 31.13 grams of barium sulfate. Okay, 31.13 grams of barium sulfate. Now let's find out moles of barium sulfate obtained. Moles of BaSO4. So 31.13 grams divided by 233 grams per mole. This was the molar mass of barium sulfate. You found it earlier, no? So no need to show that one again. Huh? Showing one time is okay. It's fine. So we rounded it off. So ultimately you are given 0.1336. So I rounded it off as 0.134. Okay, so that will be enough. So the accuracy of your answer depends on how much you simplify. So let's say in this question it's just 0.13, no? So then you need to continue a little bit more. It's better, okay? With the time you have, decide how much you simplify. So however, now this is the moles of barium sulfate. These are the moles of barium sulfate. Then we can go to the moles of sulfate or moles of H2SO4. Moles of H2SO4 is same like the moles of barium sulfate. Okay, so that is same 0.134 moles. Right, then we can take moles of FeS2. Moles of FeS2. Moles of FeS2 is half of this one, isn't it? Because one FeS2 gives you 2 sulfuric. No? Remember that ratio. You can write FeS2 to H2SO4 ratio is 4:8. That means 1:2. Isn't it? So that ratio you can use and say, okay, so half of this will be given as FeS2. So then you can find mass of FeS2 converted to, or you can say mass of FeS2 reacted. So originally you have this much of FeS2 theoretically, no? So only a part of that is reacting here, no? Right? So that one you can find out by multiplying by its molar mass. 0.134 into half into 120 grams per mole. So this one is in moles. You are multiplying that one in 120 grams per mole. Apply units as much as possible, okay? And then you can simplify and see. Now here it's 60 grams divided by 16.0 gram into 100%. 50.25. So don't just say 50, okay? So there's a 0.4, you have to think about that too. You have to consider that value also. Okay, Lamai? Understood that one. See the third one. Calculate the amount of iron pyrite required to produce 8 kilograms of sulfuric by soil microbes when the conversion percentage of FeS2 in the iron pyrite to sulfate is 100%. Now here only 50%, nearly 50% was converted. No? So they are asking what if the conversion percentage was 100%. They are asking if you want to produce 8 kilograms of sulfuric. If you want to produce 8 kilograms of sulfuric, how much you need from how much iron pyrite amount you need. Okay, so we need 8 kilograms of sulfuric. So mass of H2SO4 needed is 8 kilograms, or you can say 8,000 grams. Okay, so to obtain this amount, they're asking how much iron pyrite the initial sample is needed if the percentage conversion is 100%. Right now, let's say how to do this. So this is the mass of sulfuric. No? So let's find out moles of sulfate. Moles of sulfate. Okay, so then you need to show FeS2 to sulfuric ratio. That was 1:2. We mentioned this earlier. So therefore, FeS2 moles needed. So now the conversion is 100%. So therefore, all these FeS2 will convert to sulfuric. Earlier, it was only 50% something. No? Now here they says in the question, assume that 100% of FeS2 is converted into sulfuric. Okay. So that means we can find out the same moles by dividing this value by 2. Okay, dividing this value by 2. Then you can find mass of FeS2. FeS2 required. So you can just multiply by its molar mass 120. But this is not the final answer. Okay, remember they asked the iron pyrite how much mass you need. Okay, so then you can show mass of iron pyrite. So mass of iron pyrite will be the answer that you are getting here. You have to divide by 80 and multiply by 100 because only 80% of iron pyrite is FeS2. You have to come up to that level. Understood the method? Then let's simplify. There are many other methods you can do the same question, but this is kind of a basic way that everyone can understand. So let's divide this one by 98. Yeah, you need to show the molar mass of sulfuric also. Molar mass of H2SO4. For that will be will be given marks. 1 into 2 plus 32 plus 16 into 4. You'll be getting 98 grams per mole. So you need to divide this one by 98. Then you can show how many moles you are getting. Now this is also not divisible, so let's keep it as a fraction. 8,000 divided by 98. Then 8,000 divided by 98 into 2. That will be multiplied by, that is the number of moles, no? Number of moles of FeS2. No? So then this is the mass of FeS2 required. And then the whole thing 8,000 into 120, 98 into 2, then divide by 80 and multiply by 100 to get the mass of iron pyrite. This is the answer you need to simplify. 60 into 10 to the power 4 divided by 98. Or you can say 600 into 10 to the power 3 divided by 98. Or you can say simply 600 over 98 kilograms. This is in grams, no? So now let's divide and see. I think we can simplify this further. Can divide this one by 2. So then it becomes 49 and 300. 6.12. So my advice is don't just say 6. So how much of you got this answer? So now I'll show you the marking scheme. This is the one given in the marking scheme. See, calculating molar mass of barium sulfate and FeS2. They have given some marks. Then moles of barium sulfate finding, and then the statement, because we can't write a reaction for that, no? Not enough data. So therefore just say 1 FeS2 gives you 2 barium sulfate. Most of students got stuck in the question in the A-level exam. They try to write a reaction for this. So that's not actually something possible for this, no? So because they haven't given anything else, no? So you can't say how this is reacting. And you have no idea what is inside this FeS2. Right? So is it sulfur, which oxidation state, like that you may have doubts. So just ignore everything and see what 2 sulfur atoms are giving 1 sulfate. Sorry, 2 sulfur atoms. Yeah, if there are 2 sulfur atoms, it should give 2 sulfate. That just think about that. Okay, so you have to give that same thing in a statement at least. Okay, and then finding the FeS2 moles, mass, and then percentage. Can you understand that part, Lamai? Is that clear? Then let's go to the second part, that microbe thing. The answer we got only 50% something converted to sulfuric, that part. See the way. This is one method. So you may have done in same way, okay? So first of all, we are finding how much mass of FeS2 present. Then this answer they have given, they have gone with the barium sulfate. So they got 50.1. Yeah, this is the one we did. See, we found the moles of FeS2, actual moles. So mass 116 grams. And then we got moles of barium sulfate, moles of sulfuric, then moles of FeS2, and then experimental mass. Okay, 8.016. Then we divided that one and found we got something else, right? 50.8. Yes, I don't remember the answer, but you can check the answer we wrote. So however, this is the method we did, but our answer is a little bit higher than this, no? 50.2 something we got. Please check that one again. I think it is not a simplification error, however. Here we got the answer for like, yeah, 3 decimal places, no? We got something else, yeah. They haven't simplified in the middle, that's why. I think I did simplify it somewhere here. That's why we end up with that kind of an answer. Anyway, if our method is correct, then we will be offered marks, okay? Don't worry. And then there are other alternative methods. You can see this. Here, barium sulfate again, 50.1. And this one, they have gone with the sulfuric moles, same thing. Okay, so then that's it. Is that clear now? It's better to do the simplifications at the end, no? Then we will also get a very close answer to 50.1. Then this is the last part. So they ask how much of iron pyrite is needed to get 88 kilograms of sulfuric. First of all, find the moles of sulfuric, then show the number of moles of FeS2 required, then got the mass of FeS2. Yeah, 6.12 kilograms. We got that same answer. So you can see the reason, no? Because we did the simplification at the end, no? That's why we got the same answer as the marking scheme. Okay, but earlier question we didn't do that one. We did the simplification at the beginning. So that's why we end up with a slightly different answer, but still, don't worry, okay? And so I hope you understood the question. It's not that difficult, but it's checking something, like I said at the beginning, it is checking something more practical application of chemical calculations. Okay, now let's look at the first question. Which of the discoveries given below is Henry Becquerel best known for? So Henry Becquerel is a very easy question, right? So what is the first question, right? It's related to radioactivity. So those who answered, everyone has selected that answer. Very good. Radioactivity is the answer that Henry Becquerel is related to. And then you have other experimental findings, other discoveries. So now let's write in front of them those discoveries. Who are the scientists related to those experiments? So wave particle dual nature of matter is explained by Broglie. Okay, Louis Broglie. Write down that one. Broglie is the one who explained the wave particle dual behavior of matter. And then write again particle nature of waves. Particle nature of waves. Particle nature of waves is introduced by Einstein. Particle nature of waves, that photons are energy packets and they can behave like particles too. Okay, so that was explained by Einstein. And wave nature of matter is explained by this dual nature is explained at the end by de Broglie. Okay, remember that. The radioactivity, it's true, Henry Becquerel. And then X-rays, Röntgen. Okay, you might have heard that one. It's not there in the syllabus, however, Röntgen. And then structure of nucleus, you can write. The nucleus word was articulated by first our Rutherford. Okay, so then the scientist known for that one, Ernest Rutherford, Geiger, Marsden, you can write their names. Structure of the nucleus. So when they say structure, you can think about the neutron, proton, everything. So then kind of the one who discovered neutron is also a part of the structure of nucleus discovery. Okay, so then you can write the neutron was discovered by James Chadwick. No, so Chadwick also you can include into that answer. Understood? Then those are the other scientists. Now just a very simple question. So this again explains and I want to tell you that study that names, those names that we learned in the first unit. They are important. See, one MCQ, 1 mark. No? So if you lost this one, it's very sad, no? So that's the one, that's the answer for the first MCQ. Good. Those who answered, everyone got it correct. Then go to the next question. It's asking maximum number of electrons that can exist, maximum number of electrons that can exist in an atom with quantum numbers n equal 4 and L equal 2 in ground state. N equal 4, L equal 2 in ground state. N equal 4, L equal 2. So N equal 4 means fourth energy level. Fourth energy level. L equal 2 means D sub energy level. D sub energy level. So finally they are telling you about 4D. 4D. In 4D sub energy level, it doesn't matter whether it is 4D, 3D or anything. So you have, for D sub energy level, you have 5 orbitals. In those 5 orbitals, you can put maximum up to 10 electrons. 10 electrons. Understood? So the maximum number of electrons that can exist in 4D is 10. That's it. It's a very easy question, right? And remember, if L equal 0, it is S. If L equal 1, it is P. 2, it is D. 3, it will be F. In fourth energy level, you have 4F also. But here it's not asking for F, it's asking for D. Then don't be confused, because in 4F you will be having 7 orbitals and 14 electrons. Okay, don't get confused. That 14 I saw, that also there as an answer, isn't it? 14 is also there as an answer. Check. No, 14 is not there, so don't worry. Right? So still, yeah, answer is answer 4. Answer is answer 4. It's not asking about the total electrons, it's just asking about the number of electrons that were there. Okay, let's see how many of you got that correct. So first answer, like I said, all of you got the answer correct. Good. And then the next one, here, second answer. Yeah, majority of you got correct. It's not 18. It's not asking the total electrons. How, by the way, total electrons in fourth energy level is not 18, right? 32 electrons are there, because 4F is also present. Right. Let's go to the next question. Third one. Third question. It's asking the example best denote H bonds, ion-induced dipole interactions, dipole-induced dipole interactions, and dipole-dipole interactions, respectively. So they're asking H bonds, then ion IDP, then DP-IDP, then finally DP-DP, dipole-dipole. This is a new question, right? This was not there in past papers. So, what are the proper examples? There are several examples given. We'll check each. No, some common examples are also there. And first thing you see here is orthonitrophenol and the paranitrophenol example. So I want to explain that thoroughly. Okay, so now listen. So what is this orthonitrophenol, paranitrophenol thing? First of all, let's get their structures. So orthonitrophenol, this was there in your bonding unit. Refer hydrogen bonding part, you will find it. Okay. Orthonitrophenol means you have the phenol part here. Orthonitrophenol means this one. So basically, orthonitrophenol is this structure. Okay. And paranitrophenol is this one. In the para place, you will learn these ortho para names in our organic lesson. This is orthonitrophenol, and this one is paranitrophenol. So then orthonitrophenol, the special thing is within the molecule, they can make hydrogen bonds. Within the molecule, they can make hydrogen bonds. So we call this one as intramolecular H bonds. Intramolecular H bonds. Okay. And then there is a chance of making between two molecules also. Right? But the mainly it occurs within the molecule. And for paranitrophenol, they make H bonds between two molecules mainly. This oxygen also can, both oxygen can participate in bonding. Okay, I'm just drawing for one. Let's say like this. So they make hydrogen bonds between two molecules. So this is called intermolecular H bonds. Intermolecular H bonds. So both are H bonds, both are powerful. But when you think about the boiling point, when you think about the ability to vaporize these things, it is mainly influencing the attraction force between two molecules. Remember, if the intermolecular attractions are stronger, boiling point is higher. That's what we learn. Intermolecular attraction, if they are powerful, then it is difficult to boil, difficult to separate two molecules. It's very simple to understand. So here, the intermolecular attractions are mainly shown by paranitrophenol. So you can understand, right? So which compound, is it ortho or para, will have higher boiling point? Okay, which one will have the higher boiling point? Obvious, it is paranitrophenol. Why? Because this is the molecule, this is the compound that mainly show intermolecular attraction. Understood? So then for this one, boiling point will be higher. I'll given a small explanation at this one to your note. And if you don't remember this one, please refer the note. It is there in hydrogen bonding lesson, that topic. Okay, go and refer that one. And I think most of you remember this. However, write this explanation. Intermolecular H bonds. Therefore, IM intermolecular attractions are better. Therefore, boiling point is higher. Now, explain about this one. This is intrano. Therefore, intermolecular attractions are lower. So, less ability to form intermolecular hydrogen bonds. Right? Because they participating in hydrogen bonds within the molecule. That's not good. So, therefore, boiling point is lower. So, however, both orthonitrophenol, paranitrophenol is suitable for hydrogen bonding. So you can see all your answers are starting either one of that, no? So then, either if you don't know even this orthonitro, paranitro thing, still you can, it's not affecting the exam answer. That's what I want to say. But don't think simply. So they might ask this again, huh? Is that clear, Lamai? Any doubt on that one? Intra. And then look at the other part. You have for iron IDP bonds, I2 in Ki, HCl and argon. So kind of they are same, no? So let's investigate about other interaction types and we can come to a conclusion. First one you have is I2 in Ki. I2 in Ki. So I2 is a non-polar molecule. Non-polar molecule. And when I minus present there, it's an anion. So it can repel the electron cloud of this non-polar molecule. And then it will form a temporary induced dipole like this, a temporary one. So now it can make interactions with I minus. So this is what we call as iron IDP. IDP and iron. So the first answer is correctly showing that one. No? So then your answer can be either 1 or 4. Okay. So iron IDP. So this will be I minus and I2. Ki and I2. Ki is a ionic compound. No? So Ki is fully dissociating to give you K plus and I minus. So it's basically I minus. That's what you need to understand. And K plus also can make attractions, okay? K plus can also make similar attractions. And then the next one, HCl and argon. HCl and argon. HCl is a polar molecule. Polar molecule. And argon is non-polar molecule. So then polar and non-polar follows a similar way. You can remind that one by looking at the book. So polar and non-polar is making DPID. DPID. So then you can check fourth and first answers. So that is correctly expressed in the first answer. Fourth and first answer. Okay, so then your answer will be answer 1. Can easily select that one. To just remember a little bit about the intermolecular attractions. Okay, so refer that well. And then the last one is CLF. CLF is a similar molecule to HCl. Okay, this is it. So it's a polar molecule. So there's a dipole moment towards this side. And this one will be delta negative and this one will be delta positive. A polar molecule. So polar are making, DP interactions. DP, London, everything can be made. So however, CLF will make dipole interactions with each other. Understood? So you can refer our earlier paper class recordings. We did many questions related to these intermolecular attraction topics. And I remember this same thing was given in your evaluation test also. Remember, orthonitrophenol, paranitrophenol, there was a question from this one. So that's it. So everything there in the syllabus, you need to remember and study. Do it nicely. So answer is answer 1. So let's see how many of you got that correct for the third question. Now, okay, good. Majority of you have taken the answer. Then let's go to the fourth one. The correct order of increasing electronegativities of carbon. So it's electronegativity of carbon. Okay. So just imagine there are Lewis structures. So now this is a tetrahedral molecule where 2 hydrogen and 2 chlorine atoms present. So this is also kind of similar to that. Instead of chlorine, you have here fluorine, F. Now this one totally composed of hydrogen, tetrahedral molecule. So now all these 3 molecules are tetrahedral. If they are tetrahedral, their hybridization is sp3. S percentage is just 25%. Okay, S percentage is low. So therefore you can say electronegativity will be lower. But if you take this COF2 is a trigonal planar molecule. You get the structure. Trigonal plane. So then this one is trigonal plane. Therefore, S percentage is 33.3%. That means its electronegativity will be higher. Basically, COF2 is the most electronegative carbon. COF2 has the most electronegative carbon. So you have to select an answer that ends with COF2. That ends with COF2. Only 2 answers present. Either one first answer or the second answer. Okay, so it's very simple, right? Eliminate all other answers. Then to select whether it is first one or second one, you have to check, if you check the lowest electronegative one, that is enough. Can you see? I'll show you it in the answers. See, only 2 answers are giving you COF2 as the highest electronegative one. Then check the First lowest electronegative one, see. If it is CH4, lowest electronegative, answer is answer 1. If it is CH2, Cl2, answer is answer 2. Very simple. You don't need to arrange them in order, especially in MCQs. Okay, right. Now let's find out. So what's the next factor? So how do we assess the electronegativity? Following scope rule. So S percentage is same for those 3 molecules. See, all are having 25%. Then you go to check and charge. So all these carbon atoms are having no charge. So you can't select an answer there. So charge is also same. This percentage is also same. What about the oxidation number? This is going to be different, right? So for example, oxidation number of this one is -4. Oxidation number of this one is 0. See, from fluorine is pulling electrons. From hydrogen, carbon is pulling electrons. So lost 2 electrons and gain 2 electrons. Oxidation number 0. This one is also 0 oxidation number. So now you can see oxidation number is lowest for -4. Therefore, this one is the least electronegative compound, CH4. CH4 is the least electronegative compound. Understood? So then your answer will be answer 1. Answer 1. And then according to answer 1, CH2Cl2 is there and CH2F2 is there. So that is taken by assessing the peripheral atom electronegativity because their oxidation numbers are same. No? Then peripheral atom only difference in chlorine and fluorine. If you take the peripheral atom, fluorine is the more electronegative peripheral atom. So then central atom electronegativity will also be higher. Understood? So therefore CH2F2 having a higher electronegativity than CH2Cl2. Because you can say peripheral atom F is more electronegative than Cl. Sorry, fourth question, first one is the answer. First one is the answer. Yeah, let's see that table, how to find the answer. Question number 5. Which of the following could be correct regarding X and Y? So it says Y is heavier than X. Right, so I'll copy the table to the board. First of all, number of protons, neutrons, and electrons, then the mass number. So here X and Y. A 6 and this one is 7 and B and 6 and C, D and E. Okay, it says Y is heavier than X. That also given as an information. There also you can start the question with that. Okay. So, then if Y is heavier than X, okay, so mass number of Y is greater than that of X. So that means, therefore you can say, depending on this information, E should be larger than D. Understand? E should be larger than D. Should be larger than D. Then check your answers. If any one of them is having E a lower value than D, okay, so then it's wrong. Therefore, you can say fourth answer is wrong. Okay, fourth answer is telling D as 14, E as 13. It can't happen. Right? So very simple. Then check this one. Yeah, it's telling a number of electrons and number of electrons given. So number of electrons is equal to number of protons. Therefore, number of protons should be 6 for the X atom. And then the mass number will be the sum of these two. And that should be what? 6 and 13. 6 and 7 gives you 13 as the mass number. So then check, A should be 6. Then if A is not having another answer, it is wrong. So therefore, A should be 6 now. So then your first answer is wrong. Then our D should be 13. Okay. All other answers, D is there as 13. Okay, fine. We eliminated 2 answers. And then check if their protons are same, you can say they are isotopes. Isotopes, isn't it? Then number of protons and electrons should be same also. So then your C should also be 6. For C, you have 7 in fifth answer. Therefore, you can say fifth answer is also wrong. So now we only left it second and third answers. The difference is second and third answers is value for the B. B is the number of protons. So neutrons. Yeah. Then if it is heavier than, if Y is heavier than X, then this should be 14. No? It was given. If it is 14, this should be what? 8. Because 14 minus 6. Easy question, but don't waste too much time. So then B should be 8. Okay. B should be 8. So therefore answer 2 is also wrong. So then we left with the answer 3. Third one is the correct option. Then go to the next one. Question number 6. Yeah, it is a chemical calculation. We'll see how to do that. And then you have 2 equations. Calcium carbonate goes to calcium oxide and carbon dioxide. And Al2CO3 aluminum carbonate is also going to Al2O3 and 3 carbon dioxide. 3 carbon dioxide. Okay, 3 carbon dioxide. Then here you can say if now the question is telling calcium carbonate and Al2 aluminum carbonate undergo thermal decomposition as given below, and how much carbon dioxide is formed by Al2O aluminum carbonate when 3.34 grams of an equimolar mixture. Now this mixture is equimolar mixture. 3.34 grams are there. And equimolar means if you have n moles of this one, you will have n moles of aluminum carbonate also. That means you will get n moles of carbon dioxide, then 3n moles of carbon dioxide from this one. That's the stoichiometric ratio. So it's asking if the 3.34 grams of this sample is thermally decomposed, how much carbon dioxide will be given? Mass is given by aluminum carbonate. That's where you went wrong now. It's asking aluminum carbonate CO2 mass, not total CO2 mass. That's all. Okay, so be careful. Be careful. Right, so the first thing you can simplify is you can find this N. What is the value of N? You can find it. So you know they have 2 N moles of each compound. No? So molar mass is 100. It is given in the question. And for aluminum carbonate, molar mass is 234. So if you multiply moles into molar mass, you will get the mass. So simply you can say 100 into N plus 234 into N. This is the mass of calcium carbonate. This is the mass of aluminum carbonate. Okay, and it will be equal to 3.34. 3.34. Okay, so that means if you add them, 334 N equal 3.34. 3.34. So your N is equal to 0.01 moles. 0.01 moles. So here you will have 0.03 moles of CO2. So therefore, mass of CO2 is equal to, you can multiply by its molar mass, which is 44 grams per mole. So you will get 1.32. 132 is the answer if you multiply 44 by 3. Understood? Okay, so that's why you may have missed the answer. You may have multiplied that one by 4, some students. Those who got 1.76 or something may have done that. So read the question carefully. That happens. That happens. So not a difficult question. They kind of cleverly misguided you with the statements. Okay, let's go to the 7th question. Identify the species which has a different shape from that of NCO minus sign. A different shape than NCO minus. Okay, so what is the shape of NCO minus? Central atom is carbon. Central atom is carbon. If there is a negative charge, normally it should be there on more electronegative oxygen here. Oxygen is the more electronegative element. So this is the structure. This is the stable structure. Okay. And then you can see here, you have 2 repulsion units. 2 VSC PR units. Therefore, it's linear electron pair geometry and linear shape. So it's linear. They're asking what is not linear. That's the question. I'm asking which one is not linear. Which one is not linear? That's the question they're asking. Okay, let's see how many of you got the answer correctly. Yeah, good. Majority of you have taken the answer. Right, so NO plus, this is the Lewis structure. So it's linear. Basically, there are only 2 atoms. No? Every compound that is composed of just 2 atoms is linear. Nothing else can happen, no? Isn't it? Only 1 repulsion unit, so it's linear. And N3 minus, this is the Lewis structure of N3 minus. Or you can draw, there is a resonance of this one. You can draw that too. This was there in your evaluation test. So basically, that is also linear. And XCF2, I'll draw it here. It is also linear, but it is derived from a different electron pair geometry. Remember, this is the electron pair geometry. So trigonal bipyramidal electron pair geometry and linear shape. Trigonal bipyramidal electron pair geometry is having 4 shapes. No? Trigonal bipyramidal shape, there are no lone pairs. Then if there is 1 lone pair, you have seesaw. There are 2 lone pairs, you have T-shape. If there are 3 lone pairs like this, you will have linear. Remember, so linear shape, linear shape, linear shape. And then this one, CNO. So don't get confused with the NCO minus. If they say CNO, you must put the central atom as nitrogen here, as they expressed. So then that also can happen. Still the minus charge should be there on oxygen. So then 3 lone pairs plus minus. This is the structure. Still it is linear. So then last one must be our answer. What is the SF2 shape? It's very simple. It's just like water, right? H2O. It is bent shape. Bent shape. There are lone pairs that makes it bent. Understood that one, Laman? Easy question, but write a good review. Write a good review. The structures of these are important. When there is a negative charge, it must be there on more electronegative atom. Remember that. Okay. Then let's go to the question number 8. Question number 8. Volume of 25 cubic centimeters of 0.02 KiO3 solution was added to a titration flask. The solution was acidified using dilute sulfuric and 15 cubic centimeters of 0.5 Ki was added to that. So this reaction you need to kind of understand. So I didn't actually give the reaction to. So when you practice more, you will be able to remember this reaction. So I'll put it in the board first and explain. When we do inorganic, so from this month, December month, we are starting inorganic. So we are going to learn these reactions sooner. So what is happening is IO3 minus is reacting with I minus to give I2. IO3 minus is reacting with I minus to give I2. Understood? This is what's going to happen. IO3 minus reacting with I minus to give I2. Okay. So then here, you need to balance this one. You need to balance this one. Okay. So it says KiO3 is added. KiO3 0.02 mole per decimeter cube, 25 centimeter cube. And then from Ki, we have added 0.5 mole per decimeter cube, 15 centimeter. Okay, so we'll talk about that later. But first of all, let's balance this reaction. Okay, balance this reaction. So how do we balance this one? You can do this redox balancing using the both methods. That means oxidation number change method or half finite method. So what I prefer mostly is oxidation number change method. So let's do the balancing according to that. Okay. So IO3 minus reacts with I minus to give I2. So now especially you need to write I2 again because both of these compounds in the left side are undergoing to the same change into the same entity. So you need to write it 2 times. Otherwise, you can't do that one according to this method. Okay, so write it 2 times. Then here oxidation number is +5. Then there are 2 iodine atoms. So first of all, put 2 in front of this. So you need to change it +5 into 2. So cumulative oxidation number is +10. Here also you have to put 2 because there are 2 I minuses. I2 here. Then -1 into 2, cumulative oxidation number is -2. Then 0, 0. 0 into 2, 0. Right? So here it is changing +10 to 0 by accepting 10 electrons. Here it is -2 to 0 by losing 2 electrons. Then to balance this electron exchange, what should we do? Multiply this one by 5. Multiply this one by 5. So then the same thing should be done for the entities 2. Okay, so then you can check the charges. On the left side you have -12. So add 12H plus. And then here 6H2O. 6H2O. Understood? Right, then you can use this equation for the rest of the question, but you can simplify this a little bit further. You can see, you can add them. And this will become 6H6I2. If it is 6I2, then it is divisible. Okay, you can write this equation 6H plus IO3 minus 5I minus goes to 3I2 because you can divide it by 2 and 3 water. So my request is, this is so important for all students that are going to exam. I am asking them to memorize this equation. Okay, so it's better. You can save some time. There are specific equations like that we remember. Okay, we can balance it, but remembering will save some time. Okay, so now the ratio is 1:5. So now you can see both are reactants. Then now I'll come to the point. It's a good question. Now both are reactants. Now they are moles. To find their moles, they have given concentration and volume. So what we are supposed to do here? We're not sure which compound will fully react, no? So then we need to assess their number of moles. So we call that method as ARR method. Added, reacted, remaining. Added, reacted, then remaining. Okay, ARR method. So now let's find out their moles. So how many moles we have added here? 0.02 into 25 over the into 10 to the power minus 3. So it's like 0.2, 0.5. 0.5 into 10 to the power minus 3. 0.5 into 10 to the power minus 3. That is added. And I minus this one, 0.5 into 15 into 10 to the power minus 3 means 7.5 into 10 to the power minus 3. Somewhat higher moles, no? Then how much is actually reacting? What is the limiting reactant? So one of this one will react with 5 of this one. That means 0.5 will react with 5 times like that. So if this 0.5 is fully reacting 5 times like that, that means 2.5 of this one will react. So it is there. 2.5, more than 2.5 is there. So this is the limiting reactant. So reacted and remaining. So this is nothing remaining. So 5.0 is remaining. It's not important for the calculation. But however, what is important for us is how much of I2 is produced. So 3 times like that will be produced. No? 1.5 into 10 to the power minus 3. This is what is important for us. Remaining. So this is the I2, moles of I2. So what happened to these moles of I2? According to the question, it says this is titrated with sodium thiosulfate using the starch indicator. Okay. This I2 is titrated with sodium thiosulfate. It takes 20 cubic centimeters. They're asking what is the concentration of sodium thiosulfate. Is that clear? Now, in order to do the rest, I need to erase this equation balancing. Okay, so that means we need another balance equation. We need the equation between I2 and sodium thiosulfate. I2 and sodium thiosulfate. I2 S2O3 2 minus. They react in 1:2 ratio to form 2I minus and S4O6 2 minus. Okay, S4O6 2 minus. Yes, so you got 1.5 moles of this, no? So 2 times like that, that means 3.0. Thiosulfate will be there. So they're asking the concentration. So how do we find the concentration? Divided it from the number of moles divided by the volume. So 3 into 10 to the power minus 3 divided by 20 into 10 to the power minus 3 moles. And this is coming in decimeter cube. So what's going to be our answer? 1.5, 0.15. Mole per decimeter. Okay, then let's go to the question number 9. It's also a small calculation they gave in the place 28. We'll discuss that. Manganese fluoride can be prepared according to the following reaction. Manganese chloride. 2MnI2 reacts to form 2MnF3. It's very simple. So 2:2, that means ratio is 1:1. Okay, so it says if the percentage yield is 80%, what is the mass of MnF3 obtained when 0.1 moles of MnI2 was reacted? So we are reacting 0.1 moles now. So if one reacted, one is given. If you reacted 0.1 moles of MnF3 will be given. Okay, they have even given how to find the mass percentage also. See, so they are making it very easy. So they are asking what is the mass percentage? The mass percentage, that's the question. You are getting 0.1 moles. First of all, you have to figure out you are getting 0.1 moles. Okay, that's the important part. Then you need the mass, molar mass of MnF3 for that. Okay, so what is the molar mass of MnF3? Molar mass of MnF3. So moles of molar mass of Mn is 55, and F3 is 19 into 3. So that means 55 plus 19 into 3, 30, 57, 212. So then it's asking the mass percentage. So only 80%. If the mass percentage is 80%, what is the mass of MnF3 obtained? Yeah, so here, if the percentage is, you are getting only 80%. So actual mass of MnF3. So this is the one you are expecting. MnF3 expected. Expected is 112 into 0.1. So 11.2 grams are expecting. Theoretical mass. Okay. So 11.2 you are expecting, but you are going to see the actual MnF3 mass. So into 100%. Now let's simplify this one. Mass of MnF3 you actually gotten is equal to this 8 percentage sign you can remove, and 11.2 divided by 100 and multiplied by 80. Only 80% is given. Okay. So 11.2 into 8. 16, 9, 8. And there is a 8.96. 8.96 grams. Then go to the question number 10. Question number 10. That's a ABCD question. This is the only ABCD question you can do right now. That also some other lesson theories are included, but I'll try to explain this as much as possible for your level. And look at this diagram. It's a phase diagram, a recent theory we learned under gases lesson. This is the only MCQ they gave from gases for this year. Other years there are at least 2-3 MCQs. See that? The temperature needed to solidify the liquid decreases as the pressure increases. So that one I want to explain you fully. So now in this phase diagram, it is showing you the relationship between the temperature and pressure on the physical state of a given matter. Okay. Now here, this is C, critical point, and here it's pointed towards this direction. So B is some random point, okay, that they have marked. 1.0 atm, and it is boiling at 100 Celsius. Zero Celsius. This is the diagram. Okay, so temperature needed to solidify the liquid decreases as the temperature increases. Now, this is your liquid. This is your solid, no? So solid liquid equilibrium is maintained over this line. Okay. So now let's say you want to convert this liquid into solid. You need to cool this one, or yeah, you need to cool this one. That temperature, you can see it is decreasing. Now at this 180 m pressure, you need, so A is correct. At 180 m, liquid becomes solid at 0 Celsius. Let's say, but if the temperature, if the pressure is greater than 180, let's say it is higher pressure. See, let's say this is 1.2 m, for example, 1.2 m. So then you can see the temperature is lesser, no? According to the diagram. If it is 1.2 m, temperature is becoming lesser. Temperature is less than 0 Celsius. So then this statement is correct. See that statement again. If the temperature needed to solidify the liquid decreases as the pressure increases. Yes, it is correct. Try to understand these things will be explained in another lesson too. We are explained several theories related to this one, so that's what important for this. Okay, and then freezing point of liquid is higher than the normal freezing point at the pressures above 180. Freezing point is the same meaning as the temperature where liquid become solid, freezing point. Okay, so normal freezing point is this one. See, a normal means normal freezing point, meaning the at 180 m. So at 180 m, it is freezing at 0 Celsius. If the pressure is higher, if the pressure is increases, the freezing point of the liquid is higher, not higher, it will become lower. Understand? Freezing point will become lower because you can see it shifting this direction. Understand? If the pressure is higher, freezing point or this equilibrium point is going shifting to the left side. It happens because this line directed to the, it is left shifted graph. That's the reason. We'll explain this again in a later lesson. Don't worry. Then A is the triple point, correct? So then your answer is going to be 5. No? And the last one, at a temperatures greater than 100, pressure above 180 m is needed to liquefy the gas. That must be understood by you. Okay? That part we explain. C and D is the statements that is required for your knowledge. Okay, see that one? Temperatures greater than 100 Celsius is needed to, at temperatures greater than 100 Celsius, pressure above 180 m is needed to liquefy the gas. So let's say this is our temperature. This is our temperature. Now, if you want to liquefy that one, you need a higher pressure, right? Pressure above 180 m is required. So that one is correct. That one is correct. So D is also correct. You can see that one according to the graph. So answer is anyway answer 5. Correct options are A, C, D. Yeah. Just try to focus on the last 2 statements of the 10th question. Huh? Then there are 2 more questions came for the last 10 MCQs. Among the elements of the second period of the periodic table, the electron gain energy of nitrogen and beryllium have a positive value. What do you think, Ram? Electron gain energy simply means that you are getting one electron. So for nitrogen and beryllium, they are having a positive value. That one is correct. Why? The reason is nitrogen, if you get one electron, it will become N minus now. So this is the electron gain energy, Eg1. This will be positive. The reason is nitrogen is having a stable electronic configuration. Stable electronic configuration. So what is the electronic configuration of nitrogen? Nitrogen is having 2s2, 2p3 electronic configuration. So half filled stable. Remember that part. Therefore, it is difficult to give an electron for nitrogen. Not only nitrogen, Eg1 will be positive for all group 2 elements, group 18 elements, and nitrogen. Remember that part. So all of them will have positive electron gain energy value. So beryllium belongs to group 2. So this first statement is correct. Look at the reason they have given for that one. So we mentioned about this configuration thing. Let's see, is it given there? Yes. See, half filled and completely filled shells have a higher stability than other electronic configurations. So it is also correct. It's also correct. As a fact, we know that one. So then it can explain the first question, first statement too. So therefore, answer is answer 1. Can explain. So for example, beryllium has a complete 2s2 sub-energy level. Complete. So this one has a partially complete P sub-energy level. So that causes it to be stable. Remember that. So let's see how many of you got the answer. Answer 1. Yes, I can see all of you have taken the answer. Very good. And go to the next one. Last one. The bond angles of water H2S and H2SC decreases. Bond angles. H2O, H2S, and H2SE. So this is also we discussed under the bond angles. Bond angles. Now let's draw this one and see. This is H2O. And this is H2S. It's having longer bonds. So bond length is higher. Bond length is higher. Okay, for the H2S. And then sulfur electronegativity, central atom electronegativity is also lower. Then the bond electrons will be deviated away from the central atom. But here the oxygen is more electronegative. Therefore, central atoms are bond electrons are more closer to the central atom. You can say here, bond electrons are more closer to the central atom. Central atom. Therefore, BP-BP repulsion is higher. BP-BP repulsion is higher. Therefore, they will repel from each other. That causes a higher bond angle. In your book, you will see the bond angle is 104.5. There is a repulsion from the lone pair. That's why it was decreased to 104.5 from 109.5. But still, it's a good value. But if you take this case, its bond angle is very low. As I remember, it's somewhere around 92. Because of this repulsion from lone pair, it decreases further. Understood? So then if they tell us this bond angle decreasing, this statement is going to be correct. So H2SC will have even lower bond angle. The reason is central atom electronegativity decreases, bond angle increases. Then BP bond pair electrons move away from the central atom. Away from central atom. Now let's see the reason they have given. Electronegativity of central atom of H2O, H2S, and H2SE decreases. Yes. They have said about electronegativity. It's not a full explanation, but from electronegativity, you can explain this. No? can explain this. So then answer is going to be, second one is going to be also correct, and it can explain the first one also. Again, answer is going to be answer 1. Understood, Lam? So that's the answer for the last MCQ. Let's see how many of you got that answer. Yeah, there is some confusion for some of you. Yeah, but I think now it is clear. Bond length, and there are several factors affecting the bond angle. It's true. But electronegativity can explain what is happening here. So then you can take that as an explanation. Understood? And bond length is also affecting, electronegativity is also affecting both. Okay, so refer your book. There are more examples, ammonia and F3. There are many other examples. Basically, we did everything. So now it's kind of, we had to do papers like this just to remind the theories. Right, so I hope you understood today's discussion. We did 12 MCQs that were there in 2025 A-level MCQ paper. And then we did a essay question from 2024 A-level paper, chemical calculation essay. Right? So write a good review and bring that one to our next theory class. I'll check. And in this Friday, we'll do another paper. I'll add it to the group. Okay? Right, so goodbye everyone. Study well.